has started, no recording?
Not yet. Yeah, it started.
Yeah. So Muna, you may start now.
Okay. So welcome to the 9th lecture on Riemannian symmetric space, and actually last knowledge depends if you will ask some questions. So you are strongly encouraged to ask some questions. Okay. Last lecture actually somebody Monosda asked this: what are the examples of pseudo-algebraic groups for which associated polynomials have complex coefficients? You can check that this O2, C, On, C, Un, Sun, etc. etc. These have actually the polynomials, the associated polynomial will have complex coefficients. Now, one thing is you take example SL2R, say for instance. So you write let G is equal to say x11 plus IY11. You write that in the coordinate form x12 plus II12, x21 plus IU21, x22 plus I22. Okay. So this is a real matrix. So therefore, it will satisfy this y110, y120, y210, y22 is equal to 0. This it will satisfy this 4 equation, and determinant of G is equal to 1. So that will give rise to this equation 5. If you calculate everything, then you will get this equation 5. And you see that equation 5 has this complex coefficients. Okay. So it doesn't necessarily mean that if the group is real, then it will have real coefficients. Okay.
No, Mona, just a second. You are saying SL2R is its coefficients are complex.
But
The polynomials, actually, whatever polynomials you are taking this I, there is a this one polynomial is complex. See, the thing is, we are taking this whole thing inside GL2. That is the important thing. Is it okay or not? Manojda?
No, I'm slightly
Okay, so
confused.
let us see. So G belongs to SL2R. That means first it will have all the entries real. First entry is y11 0, y12 is equal to 0, y21 0, y22 0. This 4 equation will be there. Is it clear? Now determinant of G is equal to 1. Okay. So that polynomial is, if you really expand that in this form, x11 plus I into y11 into x22 plus I into y22 minus this thing. Okay, that will become a complex equation.
But these are 0, right? This
After
then this part will go away, right?
this part would go, but the original polynomial is contains complex coefficient initially. Okay. This
Is it mentioned in some book that this is defined? These coefficients are complex.
This defined when? This is the thing. Actually, I am deriving this. I am saying that. See, what is determinant of? See, do you agree that G belongs? Okay.
It's
G
not
belongs
only
to
defined over reals. It's, I think, defined over even Z probably integers. The coefficients are coming from Z only.
Z and this there is I term here. This, see that G belongs to SL2R. Okay. So this is if and only first. Do you agree that it will satisfy this four equation?
Yes.
Yes. Now determinant of G is equal to 1. Okay. You expand that, just determinant of G is equal to 1. What will be that? It is a different thing that after you solve it, then you get if you put this y11 0, y21 0, then this imaginary part will go away. And
yeah, so this part is redundant, right?
Not redundant actually.
Mona,
okay, so yes sir.
I am little confused. A complex A polynomial with real coefficients is also a complex polynomial.
Yes, yes.
So, actually, as he says, the second part is redundant.
Now, second part, after you solve it, sir, it will be redundant. But,
Yeah, but you begin with an, what your interpretation is, you begin with a subgroup in GLNC, GLN2C, and then it satisfies this equation, which also has I as a coefficient.
yes, sir.
Okay.
If you will take this 5 equation,
Right.
then the solution set will be SL2R. Okay.
See,
When this fellow Helgeson defines, he does it, it is pseudo-algebraic group GLNC. There exist polynomials in 2 n square arguments.
Yes, sir.
So, so little complicated. Yes. So you can view it as well.
Yes. So this you can think in later if it is not clarified. Manoj, if you can think it. If
see,
it
my
doesn't,
point is that whatever defining polynomials are that will form an ideal. Okay.
actually it is not. I am not going into those things. Okay. So we will discuss this later then.
Okay.
Where is ideal? What do you mean?
No, the defining polynomials.
Right.
So basically, this defining polynomials will form an ideal. So it will be given by an ideal in that polynomial ring.
No, I am not really. It is not that much complicated. You are thinking you are thinking in a complicated way. But let me just start something, right?
Muna, can you give an example of which is not pseudo-algebraic group?
Not pseudo-algebraic group.
Yeah.
Sorry.
Actually, this
I'm a
GL
little bit confused about the definition. So if you give some example which is not, then it would be
GL plus NR. You try it. Okay.
G
Just GL plus NR.
GL plus ANR. So you're saying this is not pseudo-algebraic?
I am not sure. I think it will not be.
See, Muna, this if this is an open set, is this an open set, right? If this is open set or closed set?
Who is saying? Who is thinking? Are you saying?
Suppose you take something which is open inside GL2 and C, then it cannot be given by polynomials, right? Then it will be a closed set.
No. Where see you are taking a group. See, it has to be to begin with a group which is given as a so it has satisfied this polynomial. So there is no question of closed set or open subset. When a group is open, it is automatically closed.
Okay, so I think
No, there must be examples which are not.
What example you want?
No, there must be example which are not pseudo-algebraic because
No, but there are many. See, for example, these connected components, or when you take the universal covering groups. There is something called universal covering group that exists for every Lie group, connected Lie group. There is a universal covering group, but whereas that need not be a matrix group.
SL2R cover. Okay, Postida, this is not a actually pseudo-algebraic group.
Right.
So this is not a matrix group, but you're saying that
no, it will be not a matrix group.
But to start with the definition that it should be it is suppose I'm starting with some subset of GLNC.
Yes, exactly. Right.
So I am saying that GLNR plus, you try it. Okay.
Yeah.
GLNR plus. Okay. This is not a very important thing. You should.
No, actually, what happened is that the definition is a little bit confused. So I thought.
Yeah.
Some example which is not.
Last lecture I was talking about this GLNR plus and this SO not P comma Q. Okay. You try these things, see whether these are pseudo algebra or not.
Okay.
Okay, so this is the thing, and so there was another question somebody asked: is it true that UN is equal to S? We have seen that UN is equal to S1 semi-direct product SUN. Is it true that UN is equal to S1 cross SUN as a direct product of proof? Answer: I said this is no. A necessary condition for direct product is that S1 should commute with SUN. Okay. And you take this thing, element of S1, first element, e to the diagonal of e to the power I theta 1 1 1, and second thing is a generic element of SUN, and you look at whether these are commutative. Okay. If you see, this is a elementary matrix. This e to the power I theta diagonal of e to the power I theta 1 1 1. If you multiply from left, it will multiply with row, and if you are multiplying from right, then it will multiply column. So you can check that. You can produce some examples for which these two are not equal. For that reason, this is not a direct product. Okay, so you can see that. And one definition is I will need this. Let G H be 2 Lie algebra over R over a field K. A linear map T from G to H is called a Lie algebra homomorphism if T of Lie bracket of x comma y is equal to Lie bracket of Tx and Ty. Okay, a Lie algebra homomorphism T is called an isomorphism if T is 1 1 and odd. Okay, so let G be a Lie algebra over a field K where K is equal to either R or C. I define this automorphism of G so that T is from G to G, so that T is a Lie algebra isomorphism. You can take this an exercise. This automorphism G is a group under composition. Okay, so let me take some water. Okay, so let us begin. So last lecture we have recall we have seen that Z of UN so I am hearing my echo. Is it my voice is my voice is clear, Mithunda?
Yes, Muna, it's clear.
Everybody has to mute the.
So recall we have seen that ZUN is equal to Z of GLNC intersection O2N. So and we have seen that MNC is equal to T belongs to M2NR. So that Tj is equal to Zt. Okay. So we have look at the left hand side. Look at side that is a complex linear map from Cn to Cn, and we are identifying with this real linear maps on from R2 to N to R2 to N. Okay. So there is some identification. Ideally, one should not write the equality, but there is some identification. For that reason, I am writing this thing as equality. Okay. So now this MNC is a. If you want to be very precise, you should write like this: Z of MNC is equal to T belongs to M2 and R, so that Tj is equal to Zt. Where Z is the map from MNC to M2 and R. Okay. And similarly, one can write this Z of GL and C is equal to T belongs to GL2 and R, so that Tj is equal to Zt. Okay. Actually, nobody writes this Z because we understand what we are doing, and the thing is, the writing becomes cumbersome. But for a moment, let us write Z. Okay. So there is a purpose for that. So first, Okay, let us take what is UN basically. UN is equal to set up all T so that T belongs to GLNC and T star T is equal to identity. Okay, now I apply this Z of UN. Okay, so first thing I will write that Z of T so that T belongs to GLNC. First thing I will write. But second thing, actually T star T is equal to identity. I must see how this what is the corresponding thing in the image actually. So see this thing T star T is equal to identity. Okay, the same thing as this is if and since J is 1 1 and 2 and linear, so this is equal to Z of theta T is equal to Z of identity. This is equivalent. Now I have given you some property like in the previous lecture. Z of A composition B is equal to ZA composition ZB. So and so I will get ZT star, ZT and Z of identity is identity matrix. So and this will be ZT star, ZT is equal to identity. Okay. Now ZT star is equal to ZT transpose because ZT is a real matrix by definition. ZT transpose and ZT is equal to identity. Okay. So this is this will translate to that. So let us write that. So that this will be ZT transpose ZT is equal to identity. Okay. So if you look this thing right hand side, look the RHS very carefully. If you look at the right hand side, you will get that this right hand side is this is nothing but Z of GLNC intersection O2N. Okay. So I am getting Z of UN is equal to Z of GLNC intersection O2N. Okay. Now this is a different proof of this fact. Z of UN is equal to Z of GLNC intersection O2N. And I wanted to give two different proofs because to clarify the concepts. And another thing is those ideas will be useful later in for both the proofs. Okay. So idea of both proofs will be used later. So as I said that nobody really likes to write that Z here. So we write like this: UN is equal to GLNC intersection O2N. Okay. So this is the thing. Now we will move to the next.
Another reason is this Z is used for center. No?
Yeah. Yes.
Afterwards, you may get because the center is contained in compact group, maximal compact group.
Yes, sir.
So I think you leave it. This is
Yeah. I will leave it, but
Yeah.
actually this is NAP actually uses this Z actually. I think.
Right.
So that's the reason actually I am also using it. But sometimes we will use this thing. Okay, for this thing. Okay, so this is the thing. Now you will go back to this something called Quaternions. So this is a very new thing, and so you should be careful about this thing. So by definition, this H, okay, this is H is equal to A plus BI plus CJ plus DK, A comma B comma C comma D. This belongs to R, and I square is equal to J square into K square is equal to -1, and Ij is equal to K is equal to minus Ji, Jk is equal to I is equal to minus Kj, and Ki is equal to J is equal to minus Ik. So H stands for the name of the mathematician Hamilton, as he discovered this quaternions. So you know that H is a skew field. That means it has all the properties of field except non-commutative. And center of H is really R. So now H is a vector space over R. And H is isomorphic to R4 because it has every quaternion has 4 real coordinates. So we borrow the topology and norm from R4. Okay. So let Q is equal to A plus Pi plus Cj plus Tk. This belongs to H. Okay. This A is called real part of Q. A is called real part of Q. Okay. Now I define this Q bar actually. This colon and equal to means this is a definition actually. It says that if it is definition. Q bar is equal to A minus Bi minus Cj minus Tk. Okay, so first property I get this Q bar is equal to Q. I call this property 1. Okay. So now second thing is real part of Q is equal to real part of Q bar. This is called property 2. Third thing is norm of Q is equal to norm of Q bar is equal to this is a square plus b square plus a square plus t square square root. Okay. And fourth thing is if you multiply Q bar and Q bar Q, this is equal to norm Q square. So this is actually.
You are just defining the norm like this, right?
Yeah, I have said that we borrow the topology and norm from R4.
Norm also from
R4. This is actual definition I should. Okay. So Q bar is Q bar square. This is actually pure computation, and I will leave it an exercise. So. Okay, so and yeah, this is done in Austin after all. The Austin after all. Okay, so I should call this. Okay, so let us write this once more. Q bar. So this is okay. This is, let us call this as this. This is actually property 4. Okay.
some continuous sound is coming. Is it from your side, Muna?
Yes, yes.
Oh,
Actually, there is actually the table is not balanced actually.
okay,
So
fine. No problem.
so this is actually okay. If you look at 4, you take Q and Q bar Q square norm Q square. Actually Q bar norm Q square into Q is equal to 1. And here you assume that Q not equal to 0. So from here actually you get that Q inverse is Q bar and by norm Q square. So this is a property about 5. So now next property is really important. So this is Q not equal to 0. So, clan. This is a b bar is equal to b bar a bar. Okay. We call this as property 6. So observe, proof is very simple. Proof, since this bar operation is R linear and R lies inside the center of suffices to show it for I, j, k. Okay. So further, see, the thing is I square is equal to -1, j square is equal to -1, k square is equal to -1. Okay. So and ij is equal to k, k is equal to I. So there are some similar multiplication properties. Okay. So by symmetry argument, it suffices to show it for I, j. Okay,
So this taking bar is nothing but the reflection about the real axis, right?
yes. Okay, so to show it only for I, j, so I will do that. I, j bar is equal to k bar is equal to minus k, and j bar I bar is equal to minus j minus I is equal to j I is equal to minus k. So I here I get the I j bar is equal to j bar I bar. Now I bar equal to -1 bar is equal to -1, and I bar this is equal to minus I to minus I. This is I square, this is equal to -1. So I bar is equal to I bar. So if I have done this for I, then I don't have to do for JJ, right? Because of the, okay, so this actually finishes. So this finishes the proof of claim. Okay, if you are not convinced, then you can do it just by calculating. So this is the thing now. 7. Okay, this is property 6. So let us see. Let Q is equal to say A plus BI plus CJ plus DK. Okay. So what is Q bar? This Q bar is equal to A minus BI minus CJ minus DK. Okay, this let R is equal to A prime plus B prime I plus C prime J plus D prime K. Okay. Now I am looking at this real part of Q bar R. Okay. So observe that to get real part of Q bar R, only I have to do component wise multiplication. Okay. If you multiply A with any element apart from A prime, then that will not constitute the real part. Okay. So I have to do only component wise multiplication. For that reason, this will be, if I will do more component multiplication, then I will get A prime plus B prime plus C prime plus D prime. And by a similar argument, this is same thing as real part of R cube R. Okay, and if you look at the middle, then that is actually middle thing. This is equal to this is QR inner product in R4. Okay, so let us write that. So what I am getting, QR inner product R4, real part of Q bar R is equal to real part of R cube R. Okay, now the thing is, this same thing as this is RQ R4. So that means I can really interchange the role of R and Q. So real part of R bar Q is equal to real part of Q R bar. Okay, so I just erase this thing. So I really call this thing 7. This is my property number 7. Okay, now okay, so okay, look at the 7 first line. So I get that real part of Q bar R is equal to real part of R Q bar. Okay, so now put Q bar is equal to P. So I will get that real part of PR is equal to real part of RP for all this R comma P, this belongs to H, and I call this property as 8. Okay. Now next property is very important. Claim this is Q R norm. So norm Q R norm. So this is called 9. Okay. So proof is so what you do that QR bar norm square result QR and QR bar. Okay, and this is by property 3, I think. Property 4. This is by 4. Okay. Now I have shown that QR bar is this thing is important. R bar Q bar. Okay. This is one of the property I proved just now. QR bar. This is really norm R square and Q bar. This norm R square is a real number, so it commutes with a Quaternion element. So I can really take to the right hand side. So I will get Q bar R norm square and Q bar is equal to norm Q bar square and R bar square. So this implies that norm QR is equal to norm Q and R. Okay, this is the proof. This says that norm is multiplicative. Okay, so this is a thing, and okay, now this is H1. You take this thing. This is Q belongs to H, so that norm Q is equal to 1. So there is a. So this is actually homeomorphic to S3. Okay. Now the thing is, this shows that we and S3 is a manifold. So we borrow the smooth structure of S3 on H1. Of S3 to H1. Okay, this is the thing. Now, so let Q comma R belongs to H1. So what is norm QR? It's norm Q and norm R. This is equal to 1. So this implies QR belongs to this is H1. Okay. Now the thing is you take Q inverse norm. This is equal to Q bar Q square. Okay. this is equal to 1. So this implies also Q inverse belongs to H1. So this says that H1 is a abstract group. So H1 is a group. So this implies I get that H1, which was isomorphic to S3, homeomorphic to S3. This is a group. Okay. Now S3 is a smooth manifold. We borrow the smooth structure on H1. So exercise. Check that the group operations on H1 are smooth. That means H1 is a Lie group. Okay. So this implies H1 is a okay. So let us see that. Let us write assuming this exercise. We see that H1 is a Lie group. Okay. Now the thing is S3. This is equivalent to saying that S3 has a Lie group structure. Okay. So now there is a interesting geometric question people ask here. Which spheres are Lie groups? Answer is your S0, S1 and S3. So this actually S0 is related to the normal algebra R, and this S1 is related to this normal algebra C, and S3 is really related to this Quaternion H. Okay.
Oh, what did you say? Normal algebra or what?
Actually, in R, actually we have a norm, right?
Okay.
And
Norm
C
equal to
actually
1. Okay.
multiplication. C is multiplication and norm both are there. Field it is a dash, and these are the only things. Okay, so you can ask little bit more general thing or topological group. So we have seen that this is really these are Lie groups, but the converse is not easy. But converse is difficult, and Lie groups. You
Converse
take
of
any.
What do you mean by converse?
You when these are precisely S0, S1, S3 are precisely the Lie group. Okay. Did you get it?
Yes, yes.
So you take any Lie group and this tangent bundle is always trivial. So this means S0 and S1, S3 has tangent bundle trivial. So there is another important question people ask. So which spheres are parallelizable? Chable. Okay, so answer is S0, S1, S3 and S7. And as I've said that this is related to R, this is actually C, this is H, and this is really related to something called octonion algebra. This is called octonion algebra or Cayley algebra called. Yeah.
So this like Lie groups, then you said topological groups also. So they are
Yeah.
also only these three?
Yes.
Okay. And what is this parallelizable?
Which this means, okay, sorry, I should have read. This means which spheres has tangent bundle trivial. Okay, this is not really related to our function. But I just said for exposition. Okay. So these 4 algebras, RCH and O, these have very very close connection to the geometry actually. Anyway, so now we come back to our case. So now you have to really little bit careful. So analogous to this complex vector spaces or real vectors, complex vector space and real vector space, you can define this H vector space, means Quaternion vector spaces. But though there is a difference that in case of Quaternion vector spaces, you have to really take scalar multiplication from right. Okay. And what is the reason for taking scalar multiplication from right? The reason is that we want to define linear operator between two Quaternion vector spaces, and the linear operator will behave like matrix multiplication if and only if you define scalar multiplication from right. So that is the main reason. So let me write it. There's real complex vectors and real vector space. One defines H vector spaces. However, there is a difference. That is, in case of H vector spaces, one needs to define scalar multiplication from right. Because the linear operator between two vector spaces will behave like matrix multiplication if and only if one takes if and only scalars act right. Scalars act from right. Okay, so this is the origin. So let me define. Let U comma V to H vector spaces. So this is definition. So a map T from U to V is called linear or H linear. If it satisfies this T of U V, first condition is there. T of U V is equal to Tu plus Tv. This UV belongs to U. Second thing is T of UQ is equal to TUQ. U belongs to U, Q belongs to H. Recall actually, it's, see in this definition I am taking this scalar multiplication from right. Okay. So okay. Analogous to this vector spaces, one defines this linear independence. This is basis, dimension, etc. in H vector spaces. Okay. So you define those things. Now, okay, so let P be a n-dimensional H vector space, and let V1, V2, Vn be a basis of V. Okay, via this basis, actually we see that B is isomorphic to Hn. Okay, so via this basis, B is isomorphic to Hn. So actually, now we want to talk about linear operator on two vector spaces, but we will be most interested in linear operators from Hn to Hm. Okay, or H actually. Okay, so let us see this first. Let T. Okay, let T from Hn to Hn be a linear operator. So let this U1, E2, En be a standard base, be the standard basis of Hn. Okay, I just want to associate a matrix to this linear operator. How do I do that in complex case?
So by standard basis, you mean 1 0 0 0, right?
Yes, yes.
1 0 1 0 0,
Yes,
right?
yes. Nth entry this is 1 and everything is 0. So EI is equal to this is 0 0 0 0 1 0 0 0. This is the ith plane. So this I is no I in this section only I will take this I and J are indices for this thing actually. For me, I convince these are not quaternion, not quaternion. This temporarily only. This because you will. This is how you see this matrix. This is how you see matrix multiplication. Okay. So I will take this Ij as indices. So how do you associate a matrix to a linear operator in the complex place? You write T is a, and you write this is equal to I is equal to 1 to n, Aij, Ei. Okay. And what is the matrix associated to T? This is nothing but n cross n matrix Aij. Okay. This is the thing. But one thing I told you that these scalars should be act from right. So I will take this is Ei Aij in this case. Okay. This Aij belongs to H. Okay. And this T is called really called matrix representation of this matrix is called matrix representative of T with respect to standard basis. Okay, so this is now similarly let U is equal to say U1 U2 UN. This belongs to Hn. So that means U is equal to what? J is equal to 1 to n. Uj. This is Ej Uj. Okay, so this Uj belongs to H. Okay. Now this actually, if I want to represent this U into column form, this is U1, U2, UN. This is really This is called matrix representation or column matrix or column representation of U. Okay. So now I want to show that whether this linear operator acts like matrices. So I want to investigate that. So for that reason, I want to look this thing. I first look at TU, action of T on U, and I look at the column representation. And I want to say that whether this is same thing as TU. So this is my claim. Okay. So this is, I will show that, let us say. And what is TU? TU is U was J is equal to 1 to N is a UJ. Okay, if I really recall this thing, T is equal to J is equal to 1 to N is a UJ. So now that will be by linearity, I will write that is equal to J is equal to 1 to N T of EJ UJ. Now, okay, so what is T of EJ? T of EJ is equal to J is equal to 1 to N, I is equal to 1 to N. So this is really EI AIJ. If you remember this thing, TEJ is equal to I is equal to 1 to N AIJ. This color is from arcs from right. So this is into UJ. Now I do a change of I interchange the sums. So I will get I is equal to 1 to N, J is equal to I is equal to 1 to N, EI, J is equal to 1 to N, AIJ UJ. Now look at this thing very carefully. That precisely says that this precisely says that if you look at the matrix representation of TU, T and TU. Okay. So now you see that those, and you can take this take this exercise. You define the scalar multiplication from left and see what is there, what is the problem. Okay, you can take that exercise. So now, okay, so let us call this as.
So the main difficulty is that they don't commute, right?
Yes. For that reason. So later we will see there are many differences. So just wait for 10 minutes probably. So you will see that. So let us call whatever that property. This was really 8. So let us call this as 10 or something like that. Okay. So from 10 actually, from 10 we'll get that. T1, T2 matrix representation is equal to T1 and T2. We'll get that. Now I really like that MNS. This is really AIJ. So that AIJ belongs to S. 1 less than I, comma J less than equal to N. So you actually, by this thing, since this matrix actually linear operators actually behaves like matrix multipliers, so that I can write that T is from Hn to Hn. I identify that set with MNH, so that T is linear. Okay. Now MNH is a vector space over R, and it has n square quaternionic coordinate. So each entry is a quaternion element. Now it has actually 4 each quaternion element has 4 real coordinates. So MNS will be isomorphic to this R4n square. So we now we borrow the topology from this R4n square to MNS. The topology of R4n square to MNS. Okay, you'll remember this thing. Now and let A belongs to MNS, B belongs to MNS. Okay. Now you take this thing, define this Lie bracket of AB is the usual way. AB minus BA. Exercise. Check that MNS is a real Lie algebra with Lie brackets defined above. Now I take this GLNH. So GLNH is T from Hn to Hn, so that T is invertible. So this we know this will be a group under composition. So clearly GLNH is a group under composition. We will see that later that this GLNH actually will be a Lie group and Lie algebra will be this MNH. We will see that, but for the moment it is just a group under composition. That's all. Now, so let exercise. So let A, comma B belongs to MNH. Okay. So you okay. So that prove that AB star is equal to B star A star. You define this B star A star analog. A star analogous to the complex plane. You take the bar of entry and then you take the transpose and you prove this thing. Okay, if you will just do this exercise, then you will see you will use various properties of this H which I have listed previously, and I think you should do this exercise. Okay, so now we will show some we'll give some differences of okay, so let me write that. So differences between this MNH and MNC. This is a very important, interesting thing. So first thing is determinant. This is the usual notion of determinant. Let A is equal to say A is equal to I0 0I. Okay. B is equal to J0 0J. This K is equal to your then AB will be the here I with multiply with J, then that will be K0 0K. Okay. Now what is determinant of A? Determinant of A is equal to I square by the usual rule, that will be minus A, and determinant of B is equal to similar J square, this is equal to -1, and determinant of AB is equal to -1. Now what is determinant of A into determinant of B? This is equal to -1 into -1. This is equal to 1. So I am getting this determinant of, and determinant of AB is equal to -1, right? And this is 1. So I am getting it that determinant of AB is not equal to determinant of A and determinant of B. This is not true. Now, so let okay, that A is equal to say something like AB. Okay. So here, okay, okay, AB belongs to H. This is not real number. This is AB belongs to H. Now two rows have actually same element. So these two rows are literally dependent. So what is determinant of A? This is equal to AB minus AB. This is equal to 0. Now I look at A transpose. The A transpose will be AB. AB. These are two columns are same. But what is determinant of A transpose? This is equal to AB minus BA. This is not necessarily all. This is not equal to 0 always. Not equal to 0 always, because this H is not commutative. So this is a strange thing, because two rows are linearly dependent, but still then determinant is not 0. Now so here also I am getting the determinant of A is not equal to determinant of A transpose. I am getting now. Okay, so let suppose A is equal to IIJJ. Okay. So determinant of A is equal to Ij minus Ji. This is K plus K. This is equal to K. So determinant of A is non-zero. I'm getting now, but A, if I take A into A of 1 minus 1, so that will give me IIJJ of 1 minus 1. So that will be 0, 0. So that means A is not 1, 1. And so this implies A is not invertible. So, but determinant of A is not equal to 0. So determinant of A is not equal to 0, but still then A is not invertible. So that means this notion of determinant is not useful. So that means we need to define another notion of determinant. Because whatever properties of determinant we want, it is not coming. Okay. So there are okay. So now second thing, determinant. Similarly, trace is not used. Notion of trace is not useful. Trace. This trace of AB is not equal to trace of B. This is clear in the one-dimensional case, because I can take A is equal to I, B is equal to J, and Ij is not equal to Ji. So it is one-dimensional case is not true, and higher dimensional case also not true. So trace is not useful. Third thing is this eigenvalue and eigenvector. Eigenvector. So this is say, now you in the complex case what you get, if suppose V belongs to say eigenspace V lambda, and if you multiplied some alpha V, this is also belongs to V lambda, alpha belongs to the complex field C. Okay, this is the thing you also always get in the complex phase, but this will not be going to happen in the thing is quaternion case. So let TB is equal to VQ B not equal to 0 and Q belongs to H. Okay. Now I want to say that whether Vr is an eigenvector with respect to eigenvalue Q. So I have applied T on Vr. So by linearity I get Tv dot R. Tv is equal to Vq dot R. So I write little bit Vr and R inverse QR. So R inverse QR. So R inverse QR may be different from Q. So here is an eigenvector of T with eigenvalue R inverse QR, which may be different from Q. So this from Q, which may be different from Q. So eigenvalue and eigenvector are not same. So fourth is this AB transpose is not equal to B transpose A transpose. This is you can take this A is equal to I, B is equal to J, and one dimensional case it is not true. So higher dimension case is will not true. So now AB bar is not equal to A bar B bar like complex case. Same argument, same A you can take A is equal to I, B is equal to J. Last thing, this you know that this AB bar is equal to B bar A bar. This is an important property in one dimensional case. So you expect that this AB bar should be B bar A bar in the higher dimension case, but this is not true. This is not true. Okay. So AB bar is equal to B bar A bar if and only if this for all. I mean this is for all. If and only A comma B belongs to this M1H one dimensional case. It's true. Now, okay. Now these are the some differences with of this MNH with MNC. So we are just will therefore there are some problems. Okay. Now only thing is is true is this is thing AB star is equal to B star A star, and you are going to use this thing. Okay, you do this exercise. Okay. So since this determinant is not really well behaved, so I recall I have really said that GLNH is equal to something like T from Hn to Hn, so that T is invertible. This was my definition. I cannot say like that A belongs to say MNH, so that determinant of A is not equal to 0. I cannot say that at this moment. So however, we'll see that there is a different notion of determinant, and by that I can say this thing. Okay. So for this moment, I just let us really define that thing first, and then you will see that. Okay. So let Q is equal to A plus Bi plus Cj plus Tk. Okay, this belongs to H. Okay. So you recall that K is equal to minus Ji. I put that here, A plus Bi plus Cj. Dk is minus dk in terms of K. I put this is J minus Ji. So A plus Bi, I take common J, C minus Di. Okay, so first thing is A plus Bi belongs to C, this belongs to C, and C minus Di, this belongs to C. Okay, so I write that is this is Z plus JW. So any, so what I'm getting, any element of any element Q belongs to H can be uniquely written as Q is equal to Z plus JW, where J belongs to C and W belongs to C. Now what I am getting, this is from here actually I am getting this H, I am getting this H is equal to C plus JC. Okay, so remember this always, this R, we start from R, and how I get C, I just add R2 plus IR. Then how I get H, I just add C, and there is an extra element J, so I get that H is equal to C plus ZC. Okay, so I am getting this H is equal to C plus ZC. Okay, so now let Q belongs to Hn. So that means Q is equal to say.
This is so far as a vector space, right?
So far as vector space, no.
Does this obey the multiplication rule also?
What do you mean by the multiple? I am just expressing this Q belongs to H uniquely it as Z plus JW.
Yes.
That's
now you take Q and Q prime and write in this form. Then you multiply using the complex like taking J square equal to -1, and then multiply these as complex numbers. Are the same as if you multiply in the quaternion?
No. That there is not. This is not
same.
Same. Actually, we will do that multiplication.
Okay.
So I'm little. So you take this U1, U2, UN. This UI belongs to H. Okay. So I write this UI is equal to ZI plus JWI. Oh, not you. I should not write here now. This UM plus this J is not the complex structure actually. Yeah. So UM is equal to, this is, don't confuse with J with this complex structure J, because this J is the quaternionic element and that J is the complex structure, capital J, this is small j. So JM plus JWM. So I write that, so Z1 plus JW1, Z2 plus JW2, Zn plus JWN. Okay. So now I write the Z1, Z2, Zn plus J, W1, W2, Wn. So this is equal to J plus JW. So J belongs to, J is equal to Z1, Z2, Zn. W is equal to W1, W2, Wn. This belongs to Cn and this is Cn. Okay, this representation is unique. Is unique. So I will take 5 minutes more. So this is okay. So like you take this Hn. Okay. We start with this Z plus JW, and you get a map, natural map on C2N by this ZW. Okay. Now there is a, okay, so there is a similar to the real complex case. So there will be some multiplication by J, and that will correspond to some J tilde from C2N to C2N. This map from C2N to C2N. We will see what is this map. or before that, you need to take some observation. So take I into j. So this is equal to j into minus I, right? Because this is non-competitor, and minus I, you can take this I bar. Similarly, you take 1j. This is a j into 1. This is j into 1 bar. Okay. Now you, from this two equation, if let A belongs to MNC, you will be able to show that AJ is equal to JA bar. There is, because the elements of A are nothing but linear combination, real linear combination, I and 1. So you will get AJ is equal to JA bar. Similarly, A bar J is equal to J. Just put in place of A, you take A bar. This is a very crucial relation. I will leave easy. This is called the star and this is called double star. Okay.
Just a second, Mona. This is so A is a matrix in MNC.
MNC. That is the important thing.
And then when you, this, what is this J? This J is J from the quaternion, right?
Yeah.
And you are multiplying by right. What is the meaning of that?
See, the thing is, A is just I times J. This is J times I bar, right?
No, but A is in MNC, right? So A is a
MNC
matrix
J,
with complex
J means,
entries.
yeah.
Now, what
A
is the meaning
MNC,
of
J means multiply every entries of A by J just. See the thing?
by
A
left,
is
right? Is there anything
left.
like left? Like it's some J times the complex numbers, right?
Yeah, A from right. Where AJ means from right you are multiplying.
No, I think that does not make sense according to your notation. You have to multiply from left only, right?
No, that is not the case. Vector space, from the vector space, you define this multiplication of A11, A12, A11. Okay.
Yes.
What is something like this J? So A11 into J, A12 into J, A11.
Yes. And I am
This,
just saying that.
okay.
No,
And
but
from
no,
left.
when you are multiplying,
Hmm?
are you treating this A1 in as complex numbers or entries in the quaternion?
Complex number. These are complex numbers.
Complex numbers, na? So in that case, here you have written JW, right? Your notation is here JW. So J is in the left.
You are messing things, right? So this, see, I am giving an example. This
like
notice,
the right hand side makes sense because J times A bar. A bar is a complex matrix again, and you are writing like J times some complex number. That makes sense according to you, whatever you have discussed, right? These two J are same. Just a second. These two J are same, right? AJ and J A bar.
Yes.
This is the J from the quaternionic field, right?
A says I, so I J suppose. Sorry, complex number suppose. This is II11. Okay. So what do you mean multiply by J? This means JI, IJ, IJ, JJ. So this will be K, and JJ. This is, I am not representing anything, right? I am saying this, if you multiply A into J, this will be J bar.
Okay, by using this rule.
By using this rule.
Yeah, so basically you are treating this as elements as like complex numbers sitting inside the quaternion. That's what I think you are using. Because this multiplication you are doing inside the quaternion, right? This Ij is equal to J times minus I. This multiplication you are doing inside the quaternion, right?
Yes, everything is done inside the quaternions.
So yeah, so whenever you are multiplying by J here, the matrix A, this multiplication are done inside the quaternion. It's not just symbolic multiplication like here, J times W. It is the multiplication you are doing here inside the quaternion.
Actually, I am not getting your point. This is
maybe it is obvious. I am making it complicated.
No,
so forget about
just
it.
do something, then it will be clear actually. By the way, I will just give the representation of J tilde, then I will stop. Okay. So what is J tilde? So I will make this J of JW, okay, and write multiplication by J. Okay. So that will be, first will be I write this JZ. Okay. So JWJ. Okay. So but I need to write this form J, something like this form. So that this will give you, so J Z bar using this star. Okay. Now this is J ZW bar using this star. Okay, so this is J Z bar and J square is equal to -1. This minus W bar plus J bar. So J tilde. So this is the map will be J tilde JW going to minus W bar Z bar. So actually this is a little bit difficult thing. Really, but it will be clear after something minus W bar Z. Okay. So this analogous to this complex thing, that real complex thing. So you will get here that this MNS is equal to really T belongs to M2 and C is equal to Tj tilde is equal to J tilde T. Composition T. And this means that T is in H linear map from Hn to Hn. It is T is a complex linear map from C2n to C2n. And what does this thing means? This means T respects the scalar multiplication by J. By J. This is the quaternion element. And similarly, you will get this GL and H. T belongs to GL2 and C. So that Tj is equal to J tilde T. So what is the map? J tilde is from C2n to C2n. This is J tilde of ZW is equal to minus W bar Z bar. So exercise, check that J tilde square is equal to minus identity. So J tilde is complex antilinear, not linear. This is a very, what does it mean? But not linear. This means actually J tilde of JW plus J prime W prime W prime, and so this is J tilde lambda J is equal to lambda bar J tilde J. This actually you can check that, and I would like to stop here actually. So we will continue this on the next thing. This will be a little difficult thing, but it will be okay in the next lecture. Manoj, do you have any question? You ask what you are
Yes.
saying?
No, that's okay. I think just here you are doing the multiplication inside the quaternion. Whenever you are multiplying by J, this matrix A, then you are performing the multiplication inside quaternion. It's not just a symbolic multiplication. That is okay. So what is the use of this? You are seeing it as a complex whatever. Can you go to the last slide? Can you go to the last slide?
I will see the uses later in the next lecture. Actually, this here, see here, there are some problems. You do not define determinant, you define trace. So it is very difficult to work inside this MNS. Okay. So we will go to complex case and we will see that how we can define determinant, and we will conclude that GLNH is a Lie group, and then we will define so-called symplectic group. So we will see that these have some connection to this so non-compact symplectic group, etc. So this is a thing. Tapendu, is it clear or no, it is not clear?
Yeah, Mohan, that's clear.
Srijanda?
Sijan is there?
He was there. It's so okay.
I don't
So
see.
Mithunda, will I stop sharing?
Yeah.